Good morning, ladies and gentlemen. How'd you like the project so far? Of course it's long. It's 2 weeks. No question. Yeah, so that is what an organized data analysis project looks like. So when I got the IRS data and the water data, and I messed around, and I didn't have a set of steps that were laid out. There was a lot of messing around, and then we had a project, and then, John De Niro looked at it last time, and he messed around. And what you're getting is something that other people have analyzed and are trying to get you to bring out some features and find some features of your own. When you actually get into doing your own analysis, the first thing you're going to have to do is actually get hold of the data, which means either collect the data and enter it yourself or read it off somewhere. And then you're going to have to do a lot of exploring that is not actually laid out in any, organized fashion. And so one of the things that I would like you to do is to do a bit of that. There is a sequence of steps that we have laid out for you. However, you have the data. Right? There is nothing stopping you from going and exploring it for yourself. The point of the project is not to turn in the project. The point of the project is to understand the data set. And so we've had students, who have grown up in California locating their own zip code in the data and seeing, what is the average tax paid in my zip code? How does my zip code compare to other zip codes and so on? Please mess with the data. That is what it's for. The project, yes, there is something to turn in, but that is, as far as I'm concerned, the secondary reason for giving you the data. So I have a few announcements to make. Announcements, that should be plural today. Sorry. So you know that there's a checkpoint on Tuesday. And so at that point, you should have done a substantial pass through parts 1 and 2 of the project. It doesn't have to be entirely correct, but it should also not be random scatter shots. We'll be looking to see roughly what you've done. And that sort of prevents you from letting it go until 2 days before the project is due. So there's a checkpoint on Tuesday, and then when is it due? The following Tuesday. All right. And so here is the next announcement. Today we will not be releasing a homework set. No homework today. There will, however, be homework next Friday, so don't leave your project too long. In fact, if you can get a bit ahead on part 3 while you're doing parts 1 and 2, that might not be the worst thing to do. So there's an instead, right? The instead is very important, and the instead is motivated by what I'm seeing in tutor office hours, my own office hours, Piazza, and so on. There is one aspect of the course to which many students are just not paying any attention. And that is the text materials, the lectures that are written out, the analysis is written out, and there are the notebooks there which you can click on interact and they go live. What I am seeing frequently is people are listening to the lectures and they enjoy them. They go to lab and they, try out something, and then they just go directly to the homework. And for the project, I think what's happening is people are going directly to the project without ever having done what I consider to be studying. Right, so without having gone through yourself and gone over what were the steps taken in the code of the lecture, what precisely does this method do, that will stop a number of the questions that we're seeing on Piazza. Is I did this, it doesn't work. Well, yeah, because it takes 2 arguments and you only gave it 1. All right, or why is this wrong? Well, it was discussed in class. Okay, so the instead is very, very important. Go through. It's not just a text. It's not just a book. There's an interact button at the top. There's a big blue button. If you click on that, your notebook comes alive. That text is a live notebook. So everything that we write is a Python notebook. That notebook comes alive. Run the notebook. Change parameters and see what happens. And copy the code over to your Python playground. We've given you a blank notebook. Copy the code over, mess with it. Don't go directly to the project or directly to a homework or directly to a lab. You will find, I know people try to avoid doing this because they think, I don't have the time. I just need to get my homework done. But I promise you, your homework will take less time if you do it this way. I am not a professor who wants students to spend massive amounts of time on her course. That doesn't do anything for me. I myself used to try to study as, shall I say, efficiently as possible. However, efficiency does not consist of trying something, getting it wrong, 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 and then posting on Piazza. That's not efficient, right? If you just read the section once, this is frequently what I have to do when I talk to students. I just pull up the section and say, here, or they go, oh, right? Save yourself some grief. Crucially, this course is not about coding. Coding is a tool to understand data. Please be looking at the concepts. Look at how conclusions were drawn from a particular shape of figure. Why was it that conclusion and no other? There is a tremendous focus on code, but the focus should be at least as much on the concepts. Okay. So please do this, and you will find that your own enjoyment of the course and your own efficiency is going to increase. All right. So I have one topic that I want to start off today. We started off a little bit. Actually, before I do that, administrative questions, anybody? The class is settling down. Yes? That is correct. When homework on Gradescope, the region for the answer is pretty important. So please look on Piazza. There is some advice as to how you should determine those regions. If you have problems, please email your GSR. Yeah. Okay. So I'm going to get going with the main business of today. We started a little bit last time, and what we were doing is called simulation. And simulation is a term for using a computer to recreate a phenomenon, and in our case, it's going to be random phenomenon. And what we're trying to do is to use a simulation to understand randomness. In a classical course, you will be using math to understand randomness. But what we're going to do is we're going to pretend that we actually have a coin and we're going to toss it, or we have some game of chance and we're going to play it, and we're going to look at the results and understand randomness that way. Later in the course, actually considerably later, I'll talk a little bit about the mathematics. But to get a sense of the amount of variability, what varies a lot, what doesn't vary that much, it is much better, we have found, to actually run the experiments, to do experiments and examine results. So we did a bit of that. Last time we simulated 10 tosses of a coin and so on. So we will increase the complexity of the experiment today. I want to remind you of what you learned last time. You learned how to select randomly from an array. The method was from from the random submodule of NumPy, so np.random.choice. It selects at random with replacement, meaning whatever it has selected, it throws back into the array in the same spot and then shuffles again and picks. And you can specify the number of times. There is an option that you can specify if you want without replacement sampling. We'll come to that next week. So we learned to use np.random.choice. We learned about if statements. Multi-line statements. If the if expression returns a true value, execute the body of the statement. If not, moved to any existing elif statement, else if. And so on. Keep moving until you find one that is true, execute that body, and then get out immediately. Don't go on to the next one. If you go through and none of the statements returns a true value, then just get out, do nothing. This I found in the class. I think people had a pretty good sense of how to deal with these. There were more questions about about loops, for loops. And so this was where you had a sequence. And in our case, I think on Wednesday, the sequences were always numbers, 0, 1, 2, 3. And for every one of those numbers, we were going to perform an action. And then we were going to present the results of that somehow. What I would like to do is I would like to start by just making sure that we understand what's going on inside a for loop. And then we will do a more significant example. So let me try this. Okay, so for has to operate on a sequence. I'll make an array, and I'll make a very boring array. Okay? How many elements in that array? Just one, so this thing should do something just once. Good? All right. How about making the array longer? Ready to go? All right. Notice that the array does not consist of numbers, it consists of items. The for statement says, go to each item in sequence. So go to the first item, that's this one, perform this action. Then loop back here, that's the loop. Go to the second item, perform the action, that's this one. Loop back. You see anything else? There's nothing else. Get out. All clear? What's your name? First name? Austin. Okay, thank you. Just to make sure. Ready? That is just a dummy variable that has no meaning other than it's Austin's name, which is a very important meaning. But for the code, it has no meaning. It could just as well be I, it could be Sam, it could be dog, it could be anything, right? We will be using I very frequently because it reminds us that it means item. Right? For each item, do something. So I will go back to the more conventional. Okay, I'd like to pause for a second, and I'd like to take questions about this. Last time at the end of class, I had some questions. I think this would have addressed them if you haven't sorted it out already. Yes?
How do you make the for loop run a function you create?
How do you make the for loop run a function you create? Wait and see. We're just about to do this. Yes?
If you use I later, does it have a value attached to it? Okay.
How do you specify the number of times it's going to run through?
How do you specify the number of times it's going to run through? That is the length of this array. It is going to perform the operation for each item in this array.
Can I make it do only like items 0 through 5?
If you wanted to do only items 0 through 5, collect the subarray 0 through 5 and use the for loop on that. So let me see. Do I have a question for you? Yeah, I actually want to do this again. Hold on a second. Yes.
Can you make it after like a column that's an array?
I'm sorry?
Can you make the for loop act on a column since that's an array?
Absolutely. You can make the for loop act on a column of a table. You can do for I in table.column, whatever column label. That's an array. And it will do it for every element of that column. This one would print all the elements in order because I'm asking it to print. But I'm just about to ask it to do something else. Okay, so we had this operation. How about actually? Remind me, is this what I had before? Yes, that was called coin? I think it was. Why don't we do... If I don't specify the sample size, it's taken by default to be 1. Let's see what happens if I do this. There is no I in this operation. Okay, so what has happened here is that 2 coins have been tossed, yes? But I didn't ask to see them. So I don't see anything. This is something I think we did last time. Now I get to see them if I run it again. Okay, I feel much better now. All right, not because it's heads, tails, but because it's different. I will say, though, when you toss coins, runs, that is tails, 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 heads, 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 they are much more likely than people think. So one of the things maybe I'll get this class to do. So I used to do this in my probability classes. I would ask students to go away, toss a coin, and write down the sequence of 100 H's and T's. Has anybody done that here? Okay, there are a few people who have done that who probably had some awful middle school teacher who made them do it. Or they've done it of their own accord, and I salute you. Okay, so then I would get back these sheets, right? With 100, we'd lay them out on a 10 by 10 grid with 100 H's and T's. And then I would go away, and I would do a few calculations, and I always knew which ones had been made up. Who wants to go through and toss a coin over and over again and write down H and T? People just write down a sequence of H's and T's. What happens is people get really bothered by long runs. So made-up sequences of H's and T's tend to have more changes than actual tosses of coins. I'm not sure I'm going to get to this with this class, but maybe. All right, that was not the point of this exercise. The point of this exercise was that this the statement, the body does not have to involve the index at all. It just says for every index, do exactly the same thing. Okay? All right, so what we're going to do now is actually, I got to show you this. So this is a pretty simple body, and it did it for February, and it did for March, and if we'd given it other months of the year, it would have done all of that as well. Every time it does one of them, it goes back and does the other one, and goes back, and so on. If you have a complicated problem and you have written your code carelessly, you can get into a situation where the thing keeps going back. It keeps going back and keeps going back. And that is called a what? That is called an infinite loop. That's bad because you use up all the memory of the computer. You're going to try not to do that. That's the address of Apple in Cupertino. Now, you don't have to worry. In Data 8, we time you out if your code is running for too many minutes, so that won't happen. But it does happen in complicated situations, and you should know the standard language and the jokes of the subject. And so one infinite loop in Cupertino is a major address in the Bay Area. Okay. What I would like to do now is I would like to I'll go back to my picture. Look at the number of heads in 100 tosses of a coin, and how many heads do you think there should be? 50 is what everybody thinks there should be, and what we'd like to do is understand exactly what that means. Okay. So we have coin, and we can do the following. What will that give me if I just stop there? Type, please. Anybody remember from last time? Actually, from the slide I posted a little while ago? Okay. That's a little memory jogger. You get an array back. If you are going to use methods in your own code, you have to know the type that they're returning so that you can do the right operation with them. So you get an array back, and it's an array of 10 tosses of a coin. Now, I'm about to do 100. I really don't want to look at 100 of them, but I will get 100 of them if I ask for it. Yeah? Okay, if I count the number of heads, what do I have to do? We counted heads last time. Yeah, it's a true-false statement. Yes? And so what do you have to do to these? there's a coding. Which ones are ones and which ones are zeros? Which ones are ones? Heads, yes, true, but in this sequence, if you're counting heads, then it's the heads that have to be the ones, and everything else has to be non-zero. Yep? Okay, so we will call this array the tosses, and then to tosses, we will apply a function, Yep, actually, why don't I run that on 10 tosses so you can see what's going on. So what happened was we have coded the results of 10 tosses not as heads and tails, but as true and false. So this is code for tail, 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 head, tail, etc., etc. Yeah. And so how do I count how many there are without going 1, 2, 3, 4 like that? I'm sorry? Yeah. np.count non-zero will count the non-zero elements of this array. And which are the non-zero elements? You've got an array of trues and falses. Which are the non-zero elements? The trues. Okay, so by the way, we're going to get I want to keep the same tosses. So what should I get? I should get, how many heads do I have? 1, 2, 4? Yes? 5? Oh yeah, there's one. Okay. Okay, the thing can count. So what it did was it coded zeros and ones, and then it counted the ones, and later on we'll see that what it actually did was it added up the ones. If you add up a list of zeros and ones, what you get is the number of ones in it. Okay, so then if we want to okay, so look at this cell. If I run that cell, what will I get in the end? Will I get a bunch of numbers? Will I get one number? Will I get a string? What will I get? Okay, good. Get one number, and that will be the count, I hope, of the number of heads in 100 tosses of a coin. And, ooh, I got 50. I am very surprised. Okay, don't always get 50. So I can stand there and I'm clicking away, and the thing that we developed in order to not have to stand there and click away is the for loop. So what we are going to do is we are going to collect this code. Yes?
How has equals to tosses automatically lets it know that
Where was I? Right here. All right? Tosses is an array. Yes? So it's a sequence consisting only of heads and tails. When I do tosses equals heads, then that comparison is done for each element of the array. Right? So for each element of the array, it's going to see is it equal to heads or not. If it's equal to heads, it will return true, otherwise it will return false. And then np.count non-zero counts the trues. All right. So what we're going to do is we're going to collect all of this into a how many should we do? How many do you want to do? 1. Okay. I always do that. That is a typing error that I have been making for years. Okay, what's going to happen if I run that? Nothing. Yeah, exactly. It's not indented. And now what's going to happen? Still nothing. Well, there is something going to happen. It's going to happen in the background. We ain't going to see nothing. Yep, so if we want to see something, we need to have a what statement? Well, yeah, print is great. Print is great. It shows us stuff. But we want to work with this. This is not a function. We have to collect all of these numbers inside an array. And so the classic way to do this is to start out by defining an array that is empty. I'll call it heads. Do you remember this from last time? There is an empty array, and we are going to append to it every single time the result of our simulation. And so why don't we take a little break here and insert a cell above and take a look at how can I add the name John to this array? np.append. Okay, so that gave me an array that has John in it. And if I look at Beatles, I still have an empty array. Yep, do you remember how to make the name Beatles contain the new array? Assign it to the same thing. So we will do instead okay. So before I run this, what I'd like to do is I would like to look at the difference between this and mathematics. So we start out by defining Beatles to be something. At that point, Beatles is a name and it contains a value. Okay. We start reading the next line left to right, but it is a very bad idea. The next thing that happens is that this expression is evaluated. And when this expression is evaluated, Beatles has this empty value. After this expression is evaluated, the new thing is assigned to the same old name. So whatever was already assigned to the name disappears and the new thing is assigned. Right? So assignment statements should be read from right to left, not like English, in the other direction. First evaluate the expression, then assign it to the name. That is how the overwriting happens. And so if I run this, now we have a change. So you've seen this before, and I'm sorry to go through it slowly again, but it's important because every single simulation you do is going to have these features. You start out with an empty array or arrays, as we'll see in a bit, of results, and then you generate new results, and then you append to the array. Okay, so what do I do to this to have this number of heads get into an array called heads? So what's happened here? This line, what happens? You end up with an array that's 100 heads and tails. Yep. Now what happens? Next line. It counts the number of heads. You have this one number now, right? I want to stick it onto something. What do? I have to do an np.append somehow. Okay, so np.append, the first argument is what I should append it to. What is the array I should append it to? Heads. Okay, if I stop there, what will I have? I'll have an error? What's the error? Okay. Last line here. What will I have? Type. It's an array. Yes? And it will have whatever heads had before and one other number. Yep. Will it be called heads? No, it's a new array. So now what do I need to do? Thank you. Okay, so we're doing this once. How about we do this 5 times? Okay. This indented body is the code that is going to be executed for each item in this array. If you want to look at heads, you just take it out of the indentation. Okay, so I am going slowly like cold molasses through this because these are the parts of any simulation. The empty array, decision about what to do for one repetition, doing that for lots of repetitions, collecting the results, and then doing something with the results. So now the results are not just printed, displayed, they're an array, I can work with them. Okay, so if I wanted to simulate this expression, what has happened is a coin has been tossed 100 times and the number of heads has been counted, and that has been done 5 times. If I wanted to repeat the experiment 10,000 times, what do I have to do to this code? What has to change in this code? So here's what I want to do. I don't want to change the number of times the coin is tossed. The coin is going to be tossed 100 times, and I'm going to count the number of heads. I want to do that 10,000 times. What changes? Yeah, the 5 changes. Yep. So just to give yourself a little flexibility, you could just write 10,000 here. What you can also do is you can set and the advantage of that is that you can simply change your number of trials by messing with this number here and not messing with your for loop at all. Okay? Which do you want to do? This way or the old way? This way? All right, good, because this is the way you're going to want to use. Okay, so if I do this, I'm going to get an array of 10,000 numbers. Yep? Anyone want to look at 10,000 numbers? I hope not. So why don't we put that thing into a table and draw a histogram? Does that sound like a good idea? All right, so we will put that thing into a... By the way, did you see that? What happened here? I deleted a bunch of stuff. Yes? Did anything happen? I ran the cell. Should we do it again? Watch. You watching? Watch this to see if you can spot a star, to see how much time it takes. Ready? Okay, here we go. That's how long it takes to do this basic code of tossing a coin 100 times, 10,000 times. All right, so what we're going to do is we're going to now collect the results. So results equals table. Okay, with columns. No, it's not toss. It's repetition, and I have 1, 2, n plus 1 in steps of 1. Okay, what will that give me? What will be in that column? Yes, the numbers 1, 2, 3, 4, up to? Up to? N, 10,000 in this case, yes, good. And then this is our friend heads. And why don't we take a look? What's the benefit of this? The benefit of this is now we can use table methods for visualization. So what does that do? Selects the number of heads column. Okay, so I'm going to do something here. I'm just going to specify some bins. They will look weird. We'll talk about them after we see the picture. Some dumb bins, never mind. It's just this histogram. And what is important to understand is what has happened in that histogram. On the horizontal axis, the number of heads, that is these values here. Yep? Okay. Each of these bins I have deliberately selected to have width 1. Yep? So each bin has width 1, and so percent per unit is actually a percent. Look at the bin at 50. This is the percent of times you got 50 heads in 100 tosses. What percent is that? It's 8% per unit. A unit is just 1. Yes? So for that single bin, you have 8%, roughly. So take that in. You said, if I toss a coin 100 times, you expect 50 heads. The proportion of times we got 50 heads was tiny. It was only 8%. Right? So the one thing you want to note is that this thing that you expect might be the most likely value, but by itself it's not very likely. Each individual value has pretty small chance. Right? You have a pretty small chance of getting 50 heads in 100 tosses. Of course, you have even less chance of getting 40 heads. So if you like, 50 is the best of a bad lot. No surprise that the histogram is roughly symmetric, about 50, because the coin is fair, heads and tails have the same status as far as probabilities go. And now I want you to, we start out always looking at the horizontal axis. Do you see that I ask for the bins from 30 to 70, roughly? If you toss a coin 100 times, how many heads can you possibly get? What's the smallest number you can get? 0. What's the largest number you can get? 100, yes? Can you take a look at the probable numbers? What are the probable numbers? Well, I'm looking at here, this is about 35, yes? And that's about 65. You see anything outside that range? Not really. We have 10,000 repetitions. That's a lot of repetitions. And in those 10,000 repetitions, we didn't pick up hardly anything outside of 35 to 65. That's another thing to take in from this picture. Though the possible range is 0 through 100, the probable range is much smaller. It's only 35 to 65. That's 50 plus or minus 15. Agreed? And if I just look at 50 plus or minus 5, if I go from 45 to 55, that's nicely on here, I pick up the bulk of the data. So in fact, if you toss a coin 100 times, you are quite likely to get a number of heads in the 45 to 55 range. You are almost certain to get a number of heads in the 35 to 65 range. And everything else is highly unlikely. And having done the math for decades, and having taught the math for decades, of course I knew that, and that is what allowed me to cheat and set the bins ahead of time. I knew I was not going to get anything outside 30 to 70, no way. Okay? And so what you have here is a more physical understanding of something that seems to be a rather dry probability problem when you're tossing coins. But when you are assigning a group of, say, 100 men and 100 women, 200 people to, 50 men and 50 women, 100 people to treatment and control, yes, you'll be tossing 100 coins, say. What you've noticed is that the groups might have a 45-55 split. They need not be equal. Yes? If you have 100 people and you toss a coin and you put the heads in treatment and the tails in control, well, the coin is unlikely to give you 50-50. Only 8% chance, 92% chance that your groups are going to be of different sizes. Yep, so you should not be insisting that your two groups are of equal size. The point is that we understand the mathematics of this and we understand the simulation of this. We can account for the different sizes because we understand the randomization, and we'll be spending some time doing that. Okay, so I've spent quite a lot of time on this because it is an important example. This has the germ of everything that we're going to do. What I'm going to do next is play a game. That is a very well-known game. And we're going to see what you think of the game. Okay, so I'm going to stop for a second. I'm going to take questions on this, and then we're going to play an actual game. Yes? What select does is it selects the particular column. So if I had written select number of heads, it would have selected just this column, because I want a histogram of just this column. What I've done here is I've used the index. This is column 0, this is column 1. More questions? All right, we're going to play a game. And this was a television game. It was called Let's Make a Deal. And it was a famous game show in the 1960s, and it has had numerous spin-offs. And the way of choosing something so that you get a prize has engendered more acrimonious, angry, mathematical discussions at cocktail parties than you can imagine. Everybody believes that they are right and the other person is wrong, and lots of heads get bashed in, well, metaphorically speaking. Even mathematicians have been a little nervous about this answer. However, the answer is very, very clear. And before you understand the answer, you have to understand the question. So Monty Hall ran a game called Let's Make a Deal in the 1960s. And in the end, what would happen in that game is that there were prizes available to the contestants. And the contestants had to make a choice. And depending on the choice, they would either get a prize, which is a good thing, or something that was called a zonk. And you'd rather not get a zonk, because a zonk was something like a goat. Now, we've maligned strawberry, and now we're going to malign goats. But apparently you don't want a goat. You really don't want a goat. And so the Monty Hall problem is this. It's basically a distilled version of what happened in the game. Now imagine yourself as the contestant, right? You've come to the end of the game. Here is what is in front of you. There are 3 closed doors. You cannot see what's behind them. What you know is that behind one of the doors there is a car, quite a nice one. And behind each of the other 2 doors, there is a goat. Okay? All right, you're trying to get the car. So you get to choose your door. So there are doors 1, 2, 3, and you kind of scratch your head. You can't see anything. They look identical. And you go, okay, I choose door 2. Okay? Great, you choose door 2. That door does not get opened. Do you agree that whatever is behind that door that you chose, it could be a car or a goat, yes? There are 2 other doors. Behind at least one of them, there has to be a goat. Do you agree or disagree? You agree? Okay, so what Monty is going to do, he's going to say, okay, the other doors that you could have chosen but didn't, one of them has a goat behind it, maybe 2 of them do. I'm going to open one and show you the goat. Okay? And then what you are looking at looks like this. Your original choice was door 2. Monty said, fine. He opened door 3, and behind door 3 was a goat. And now he's nice to you. He says, you don't have to stick with door 2. You could switch. You have 2 doors to choose between. And you have to now pick one of those 2. And whichever one you pick, that's the one that's going to be opened. And what's behind it, that's what you get. All right, how much time do we have? Oh, we're good. We're good. Okay, I give you 1 minute to talk to your neighbor. All right, ladies and gentlemen. So I've been to many parties where this discussion starts and it never ends, so I have to take charge here. Okay. My first question to you is, what is behind these two doors? A car and a goat. Yes? One of the doors has a car behind it and the other one has a goat. Right? Next question. Does it make a difference which door you choose? Okay, so let me tell you what I just heard. I heard, yes, yeah, yes, wait. And then, I mean, and then I burst in. That's exactly what happens every single time. All right? Okay, let me ask you a question. By the way, we should just be sure that while all this is happening, nothing is switching around back there. Right? The goats are where they were and the car is where they were. Okay. Imagine this door shut, right? You picked this one, right? You didn't know where anything was, right? What do you think is the chance that the car is behind that one, the closed one? Sorry? 1/3, right? You picked it, right? Chance 1/3, you were right. Yes? Okay. So the chance that this one has the car is 1/3. Where else could the car be? Here. So the chance that this one has the car is? It can't be 50. It can't be 50. It's 1/3. This is the remainder. The car can't be anywhere else. If the chance that it's here is 1/3, what's the chance that it's here? Huh? Okay. Now, this is why we're discussing randomness in a physical manner, because look at what's coming out. Okay. It's still, the chance that it's here is still 1/3. So then I have a total chance of 2/3. What happened to the other third? I can't give you a chance. All right. Shall we play this game? Indeed. That is a very simple and elegant answer. Thank you. But I will tell you, I've been trying that answer for 3 decades now. It is not convincing. Your colleagues are not convinced here because I gave them 1/3 and now it has to be 1/2. How about we play this game, shall we? All right? We have cliffhanger. We'll play it on Monday. All right. What? Now? All right. All right. Do you remember this function, the other one? Yes? Okay, here are my doors. Car, goat, and goat. Yes, I've got an array of goats. Goat 1 and goat 2. This, trust me, is a function that plays the game. And if you play it once, you get what you selected, what Monty threw out, and what remains behind the other door. Okay? I'm going to play it again. What remains behind the other door, ladies and gentlemen? Just keep watching that one. This is what you originally selected. This one's always going to be a goat. You're watching this one. Should we do a for loop, maybe, instead of doing that? Okay. So we are going to collect our results. So all we're doing is playing this game. Right? And everything else that's happening is we are collecting results. We played 1,000 times. You good? So this plays the game 1,000 times. This collects the results. And how about we do results dot select 0, 1, 2. How about we do a bar graph of this one, shall we? That is the remaining door. Okay. Hello? What was the problem? What? I'm not dividing anything by 0. Maybe I didn't run something.